recall the pace, yesterday's story, we started from a 3D problem, okay, which is Q-symmetric, so it simplifies. It's a pure bending problem. And I introduced the asymptotic expansions technique, and we started to derive, let's say, the leading order plate theory which come out from asymptotic expansions. So I recall that asymptotic expansions, the idea is that first you rescale your problem so that your problem depends, the full problem, the 3D problem depends explicitly on a small parameter, which is the thickness divided by the span of the plate. So the full solution is an expansion of this small, a kind of Taylor expansion of this small parameter. And you inject this expansion inside the equation of the full problem, and what you find is that you have a series of differential equations or boundary value problems which you need to solve recursively in order to solve each order. So yesterday we did what I call low order displacement, and the significant result from this first calculation is that the leading order displacement which come out is Kirchhoff assumptions, meaning that the out-of-plane displacement is just a rigid deflection, or not rigid, but it's a deflection which is uniform to the thickness of the plate, and the next order is related to the rotation of the normal fiber. Okay? So I just re-show this is the deflection for U minus 1, and this is a kind of, it is related to rotation for U naught. Okay? So these two problems were related to strains which should be set to 0. Okay? And now we are arriving at the first, let's say, significant auxiliary problem, in which we will have actually stress and strain distribution, because there are no strain or stress related to these low order displacement. Okay, so this is the first auxiliary problem. So I gather the equilibrium equation of order -1 and the compatibility condition, boundary condition, and constitutive equation, so that I have a well-posed problem. And if you look carefully, so this is the intrinsic notation, and this is with the indices. If you look carefully to this problem, it's a problem which is the only unknown. I mean, the only coordinate is z, okay, and the only how will I say? It's a problem only on the z coordinate, okay? So you have an equilibrium equation. The derivative is only on z, and for the divergence and the strain, it's also only on the normal coordinates, and the boundary conditions are at the top and the lower face of the plate. So if we look more closely to these equations, what we see that you have an equilibrium equation which deals only with the transverse stress, transverse shear and normal stress. You have the classical 3D constitutive equation relating the stress to the strain of order 0. And now, from the previous solution, from this result, we inject this information inside the definition of the strain, and what we see is that the in-plane strain is directly proportional to what we call what we will define as the curvature tensor. Okay. So the plane strain is directly proportional to the curvature tensor and is fully determinate in this problem. However, the unknowns are U alpha, U1 alpha, and U3 and these are the unknowns of the problem. And the only boundary condition we have is that you have free upper and lower faces. Okay. So, if we might see this auxiliary problem is fully parameterized by this curvature tensor, and this is only a function of the in-plane coordinates. Okay, so it's here in this problem it's as if it were constant. Okay, so thanks to variable separation, and what is interesting is that you see that the in-plane strain is just a linear distribution through the thickness of the plate. All right. So what we will do is right now is just to solve this problem. It's quite easy. You can do it by hand analytically because it is an ordinary differential equation since there is only one coordinate. So let's start with the equilibrium equation. You have this. This is the divergence, and so you see that the transverse, the out of the transverse stress are simply zero because of the boundary condition on the upper and lower face of the plate. So we have only in-plane stress. Okay, and this is very intuitive, and actually this is where people who derives Kirchhoff love plate theory from an assumption on displacement and the principle of potential energy have difficulties because they cannot see that it is actually in plane stress instead of plane strain. Okay, so we are in plane stress for the leaning order stress, and now I can write the constitutive equation. So if I recall that I have separated the in-plane components from the out-of-plane components, and I have this, those zeros comes from the monoclinic symmetry of the plate. Yes?
How is the displacement in this zero order?
I will compute it later on.
Yeah, okay.
And you can see that we are actually, you have the Poisson's displacement. Does it?
The Kirchhoff law will have shear. Shear, yeah. Vertical shear.
No, in Kirchhoff, if you assume Kirchhoff kinematics, so typically the Kirchhoff assumption is Ui is minus C with my convention and U3. Okay. If you compute the strain related.
Not from constitutive equation, but this Lagrange multiplier you get.
Sorry.
You don't get from the constitutive equation, but you get as Lagrange multiplier the shear. Of the moment tensor. So just to see if there is any compatibility in the if you have zero shear stress.
Yes.
To see if you have exactly both the Kirchhoff.
So what will come out here is that the shear stress at this order vanishes. Okay. At this order, of course, all the point of this asymptotic expansion is to go higher order and to capture those shear effects. Okay. So at this order, so the order of Kirchhoff law theory, we are in plane stress, and you can write the constitutive equation. I've put here what we know about the plane, the in-plane strain, which is linearly distributed. Okay, I detailed all the components, and those are unknown. Okay, you can readily see that the transverse shear strain are zero because of the uncoupling. Okay, and the last things to be determined is the normal strain. Okay, and the normal strain is determined by this line. Okay, and you can see that it is if you multiply this line times this line, you see that you can express the normal strain as function of the in-plane in-plane strain and as function of the curvature directly. Okay, so I just write this on the next slide. So I just recall that the in-plane strain is the linear distribution of times the curvature tensor. The transverse strain is zero, and the normal strain is related to a Poisson effect, linearly distributed through the thickness. So the out-of-plane displacement won't be zero. Okay. So now that you know explicitly the strain, you can compute the stress. we know already that the stress is in plane, and actually it is related. You can from this you compute the you compute you multiply with the 3D stiffness tensor, and you realize that actually you can express the in-plane stress as Z times the plane stress stiffness tensor. Okay, so this is a new notation. This is those tensors are localization tensors. Okay, it's a fourth order tensor. You construct twice with the curvature, and you get the local stress tensor. Okay, I'm not sure if I'm completely clear on that point. And this localization tensor has two. It mixes the dimension because the first in this is this one and this one. They are 3D. Okay, so I will write it on the blackboard. It might be clearer. So this localization tensor, which gives you the in-plane stress, the stress as function of the curvature, is ij alpha beta. It's a tensor mixing 3D and 2D. Okay, because you want to contract with the curvature. It's just the linear superposition, and you will end up with a 3D stress tensor inside the plate. Okay, is this clear? Because maybe it's not. I'm not sure if it's completely obvious. And actually this definitions, you retrieve the definition of the plane stress tensor, the plane stress stiffness, okay? So now we have the strain, we have the stress at this order, and we just easily compute the displacement distribution related to at this order, and it's simply you just simply integrate the definition of the normal strain. You integrate this function, and you can express the leading at this order the displacement field. The in-plane displacement is 0 because we know that because of the skew symmetric of the expansion, those are 0, and the only new contribution are those two guys. This is the Poisson. This is the Poisson effect, the out-of-plane Poisson effects related to the bending. So basically, when the plate bends, because this is under tension, it gets thinner, and because this is under compression, it gets thicker. Okay, and you just integrate this strain as the out-of-plane displacement. So this is a signification, and so this is a displacement localization tensor giving you the out-of-plane displacement as function of the curvature. Okay, at this order. Okay, we just contract, and those contractions are just the basic use of the superposition theorem. Okay, in linear thanks to linearity. And we need to normalize. I mean, there is an integration constant which is unknown, and we choose to normalize this to average out this distribution and to add explicitly this integration constant. And there is an arbitrary choice for this integration constant. Okay. So this is it for the auxiliary problem. I just give you, I just detail the result for an isotropic material. You recognize the out-of-plane Poisson effect and the trace of the curvature for the out-of-plane strain. Okay, and you recognize the plane stress stiffness tensor for expressing the in-plane stress as function of the curvature. All right, and the displacement, the out-of-plane displacement, you have this quadratic distribution of displacement which is related to it. Okay? So I've solved the auxiliary problem, which is a problem as function of the z coordinate. Now, in order to have a plate model, I need the microscopic problem, the plate problem to solve. Okay? So following that, I need to introduce And this, this plate problem will enable the determination of this U3 minus 1. Because, I mean, we've done all this work, starting from the very first displacement we found is U3 minus 1. It's the leading order displacement. And we've been through 3 orders in resolution, okay? And this is the unknown we are dragging from the beginning, okay? And we want to solve it. And for solving U3 minus 1, we need a plate equation, so an in-plane problem, okay? So I introduced the resultants, and actually I did it yesterday starting from an ab initio plate theory, just introducing resultants and equilibrium equation. I found a way to build a plate model. So I do exactly the same, but I select the correct orders for the bending moment at this order. So I'm integrating through the thickness sigma naught. And I need the first order shear force. So I need to integrate through the thickness sigma 1, which is unknown at this stage because we solved for sigma naught. Okay, this is sigma naught which is determined. And we know that why we need to look for sigma 1 is just that because we know that sigma 0, the transverse shear strain at this order is 0. Okay? So I define this as the shear force. And we do exactly the same trick we did yesterday for the equilibrium equation. So you see that you can find, integrating the equilibrium equation at this order, you find that the shear force of order 1 is the divergence of the bending moment of order 0. And you find that the equilibrium for shear forces is the classical one, but it's for shear forces of order 1. And of course we know sigma naught, so this will be determined, but we don't know sigma 1 because it's the next order. So we substitute Q alpha and we get the famous equilibrium equation for Kirchhoff-Love Kirchhoff-Love plates. Okay? This is the second divergence of the bending moment plus the out-of-plane force. This is the Kirchhoff-Love equilibrium equations. Okay? This one. So I have resultants. So I have generalized stress. I have the curvature because we've seen it coming out from the asymptotic expansion. What I need is the constitutive equation, and I'm done. Okay. So the constitutive equation is very classical for those who are doing asymptotics. You just compute the actual bending moment related to sigma naught we just determined solving the auxiliary problem. And you find that since this guy is linearly proportional to the curvature, and the curvature is independent of z, you can factor out the curvature and you find the constitutive equation relating the bending moment to the curvature. All right? And here you find that the bending stiffness is the integral to the thickness of v square times the plane stress stiffness tensor. And just for those who are more familiar with beam theory, if I compute z squared times E being the Young modulus, I will have 1 over 12 E. And the 1 is because I undimensioned I have a non-dimensional problem, but if I were with physical variables, I would have T cubed over 12 times E. Okay? And you recognize the second moment of inertia. All right? So if I gather all equations, this is the equilibrium equation we just derived. This is the constitutive equation we derived there. And this is the curvature. And I have those boundary conditions. We found them yesterday afternoon. And this gives me the Kirchhoff-Love plate equations and the Kirchhoff-Love theory. Okay? So this is the leading order of the asymptotic expansion. So I can solve this problem. Actually, with finite element, it's a bit complicated. You need some people relax the the relation, because you need to be in H2. You have twice these differentiable functions, and it's a bit difficult, but I won't dwell on that. And I'm happy I have a plate model. Once I have solved this problem, which determines the deflection, the leading order deflection, I can reconstruct the displacement, and it is I just collect let's say the Kirchhoff kinematics, so the deflection and the rotation, and I can have an approximation of the strain. So I collect the terms. This come out from just the auxiliary problem we just solved. Okay, so this is the strain, and it's related to the curvature. And I have an approximation of the plane stress, the in-plane stress. Okay, as follows. Okay, and what you see is that at this order, the transverse shear and the normal stress is 0. Okay. All right, so I'm done with that. Note that these kinematics comply if I say on the boundary, if I assume that the plate is clamped, and the clamped boundary condition are such that this is actually 0 on the boundary. Okay, because you set U3 0, and you must block the rotation on the boundary. So this approximation of the displacement field is fulfills the clamped boundary condition. But you could use the small corrector related to the out-of-plane Poisson effect to have a better approximation of the displacement field I just discussed. Okay. But the problem is that first you don't know this U3-1, which is the higher order deflection. And this guy doesn't comply with the clamped boundary condition. It's not 0 on the boundary, because you cannot set the total curvature tensor is not set to 0 on the boundary. Okay. So I could stop there, saying that I'm happy, but as an engineer, I am not happy at all, because actually this is really annoying me, and it frightens the students when I say, okay, the shear strain is 0, but then there is no shear force. How comes? You cannot satisfy the equilibrium. It's quite funny when you are teaching beams and plates. And I really want to know about that. Okay, this is really important. For two reasons. Okay, you would be happy to have a higher order deflection, because typically in application, and I will show this application at the end of the lecture, when you deal with sandwich panels, you have a very compliant core which is sandwiched between two stiff skins. You have this is the core. It's very compliant, and you have the two stiff skins, and it's very easy to shear. Okay, and usually you want to have this part as light as possible to spare weight, and those as stiff as possible. But of course, if this is 0 stiffness, it's not. It's no more a plate. It's you have two plates, two individual plates. In French, we say bilam. I don't know how we would say in English. And so you need to have something, but not too much. And there is kind of trade-off for designing this core. Okay. It turns out that since you wanted to have it very compliant, it is easy to shear, and this might really contribute to the total deflection of the plate. Okay, and we want to capture those effects. But okay, those effects are depends on the square of the slenderness. I mean the shear deflection. You have the bending deflection, which is determined by Kirchhoff law of plate theory. And if you want to capture shear effects related to in this situation for sandwich panel, those effects are decreasing very fast with the slenderness of the plate. Okay, so it's not always relevant to seek for thick plate theory just for capturing the shear deflection, which is very often quite small. But in some application, it's not so small. What is really important for engineers is the actual shear stress distribution inside the plate. This is really important. Okay. And this information is missing here. So this motivator is going higher order. All right? So this exploration will lead me to the bending gradient plate model in the end. So shear effects. So I go to the next order, so I collect all the equations of the next order. Okay, I will be slightly bit faster on the resolution of this auxiliary problem. Again, you have those equations, which it's a problem dealing with only the z coordinates, and this is fully parameterized. It's not obvious here by the gradient of the curvature tensor, of the curvature tensor. Okay. What is new here is that in the previous auxiliary problem there were only one contribution, which was the divergence of sigma 0 with respect to the z coordinate. Now the unknown is sigma 1, and you take its divergence with respect to the normal coordinate, but you have a loading which is related to the variation of the previous stress field we just determined. Okay. So this is a very critical, a very new feature of this new this auxiliary problem. Sorry, and you have a contribution also in the strain. It is you have a preload really coming from the strain, but this is quite the same feature as in the previous auxiliary problem. So this is expressed directly as function of the with indices. We already know that the in-plane, the U1 alpha will be 0 because it's in-plane displacement, and at this order, this guy vanishes. We already know that it is 0. And the unknown is U alpha 2 and U3 2. Okay? And we know that U3 will be 0 because at this order, this one vanishes. Okay? So actually the relevant equation will be this one, the one dealing with transverse shear strain. Alright? So we solved explicitly this problem for the shear, because this is when things are interesting. So I just reproduced the equilibrium equation. You see that the unknown is sigma 1, okay, and it is related to the transverse shear of sigma 1. And it is loaded by this guy, sigma naught, we just determined previously. But you take its divergence with respect to the macroscopic coordinate, the in-plane coordinate. All right, alpha here. And so if I explicitly, if I detail this loading, it is actually, so it just, I'm substituting what we just derived, the localization tensor times the curvature, the curvature, and you take its divergence. It turns out that this guy does not depend on alpha because it's only a function of z. So the derivation will be carried on only the curvature tensor. So you can these factors out this way. It becomes a third order tensor, the gradient of the curvature, and times the localization tensor. You contract 3 times. So this is a vector, and this is it is a force, because it is the loading of the equilibrium equation, so it is a body force. This body force is just related to the variation of the curvature tensors. Okay, so when the curvature tensor varies, this generates an unequilibrated state, and this unequilibrated state must be equilibrated by this higher order shear stress. Okay? So now I can solve, this is just, I want to capture the physics and the mechanics. Now you can solve this. You find that sigma alpha 3,1 is just the primitive of the loading. Okay, it's pretty simple. And you see that at this order, so we have derived the transverse shear stress at this order. If you look at the constitutive equation, we have this. This is from the auxiliary problem. The only unknown were the transverse shear strain, and the other strains are 0. We know that from the auxiliary problem, and this tells you that the in-plane stress is 0. So this sigma 1, which is so the stress of order 1, is purely transverse shear. Okay, because of the uncouplings. So I define a new localization tensor. This guy is a fifth order tensor. Sorry about that. We'll go up to 6. All right. And again, like before, we had sigma 0 is with it's the fourth order tensor times the curvature, and now we have sigma 1, and I note it that way. This is the gradient of the curvature. I contract 3 times, okay, and I get second order tensor, okay. So what is not yet explicit here is that I will denote second order tensor this way and a third order tensor this way. Sorry. Okay, this is already known, and this is a new notation. Okay. But the only point is that I just want to apply superposition theorem for all the components of the gradient of the curvature. Okay, that's just what is behind. So I could stop here, but it's also possible to derive the displacement field at this order. Okay, so U2, and actually I don't give the detail because it's already a bit tedious. But what you see is that you have the rotation of the higher order rotation, which came from the integration constant of the previous auxiliary problem, and you have those guys. So this displacement localization tensor, which is proportional to the gradient of the curvature, and its mechanical meaning is that it is related to transverse shear warping. So it's an in-plane displacement. It's purely in-plane, and it's just the distortion related to the transverse shear. So we see what is the physical meaning is that you have some function like that for u alpha for the displacement, and this is because of the heterogeneity through the thickness. You have those oscillation, and this is encoded in this localization tensor. All right. So this is it. So I'm happy because I captured something related to transverse shear effects. Okay? And I will be able to somehow derive a transverse shear energy. Alright? So, okay. We played the game. We can go in any order you want, higher and higher. And it's an endless game. We derived, in the presentation I derived the leading order displacement, the rotation, the effect, the transverse Poisson effect, okay, related to the curvature, and we just discussed the in-plane warping related to the gradient of the curvature, okay. Here implicitly you have a double sum. This is not obvious, but I'm sure Claude understands what I mean. You have actually a double sum in orders and in order of differentiation, okay? And but I think I won't give more detail, but the idea is that you can decompose your displacement in the following way. And we just discussed that the stress, you can decompose it in the following way, and going higher order. So this guy is the stress related to the curvature tensor. So this is the in-plane stress because of bending, and this guy, we just derived it, is the transverse shear strain related to the gradient of the curvature. All right. Sorry, inevitably it becomes complicated.
Sorry.
Oui?
Can we see again SK Nabla?
Of course. SK Nabla. It is this one. So it's just a fifth order localization tensor, which gives you the in-plane, the transverse shear stress as function of the gradient of the curvature.
So it's written down.
And it is fully detailed there. You see that the in-plane part is 0. The transverse shear part is this guy. We just integrated the loading previously, and the out-of-plane part is 0. Okay? And the 3 indices at the end is just for contracting with the gradient of the curvature. All right? At this order, it's not necessary. It's at the next order, contrary to 3D media. In 3D, or if it's a membrane theory, you need to subtract the resultant, but you don't have resultant at this stage, actually.
Why do you choose -1/2?
Because it's free at the bottom, and you can check if you integrate that this vanishes for ±1/2. You can prove it analytically. But it's, I'm not surprised by your question. All right. So this is this is the game of asymptotics, but this does not give you a plate theory. Okay. And I've missed something. You remember for Kirchhoff law, I said I have an auxiliary problem. I solve it, and I found that you have the plane stress, and I ended up with a plate problem. Okay, remember I found the Kirchhoff law plate equation. Turns out that at this order, for the transverse shear auxiliary problem, there is no plate theory. There is no macroscopic problem to be solved because of the symmetry of the problem. I don't want to give too much details, but there is no problem. And if you want to find a macroscopic problem, so a plate problem to be solved, you need to go another order higher, which is painful. Okay, and here we had the gradient of the curvature, okay, in this one. If you go one order higher, you have the second gradient of the curvature, okay? And it turns out that the macroscopic plate problem you will have to solve involves the sixth derivative of the leading order displacement field. So I'm an engineer, this is painful. Okay, and life is not as regular as that for me. So if you follow the asymptotic expansion procedure rigorously, it's just impractical for normal, low-level guys. All right. Now, what you can do, and this is suggested by Mishlayev and Chernyshchenko in in a periodic medium, and they had to play nasty tricks in order to derive this result, is that you can use this expansion and say, okay, this is the shape of this will be my enriched kinematic. Okay, you can inject this displacement field, which is compatible. Actually, inject this in the minimum of potential energy, and it works well. And Shmishelyev and Chernyshchenko, they proved some convergence. They have some convergence results with some tricks because they are dealing with periodic media, but. I think that we could use the same tools to prove higher order convergence using these techniques for a plate model, but my problem is that I still need a very high regularity for the deflection, which is still force differentiable. Because why I'm complaining, it's not a matter only of regularity, it's that I have very nasty boundary conditions. Okay, you know that we need to remove the tangent gradients and so on, and you have 4 integration pipette to perform on the boundary. Okay, so this is nasty for me. So I will try to convince you that somehow the bending gradient theory this is one reason for choosing this approach, is that you can keep very low regularity of fields, and I will have the deflection will be only C1, and I will need a new kinematic degrees of freedom for this. It's like relaxation like in a Reissner plate model. Okay. So let's try to derive the bending gradient theory. So the main conclusion of my big effort of doing this asymptotic expansion is just to show you that we can do that. It's interesting to share this with you. But the only interesting information I want to keep from the asymptotic expansion is that I can have an interesting approximation of the stress in the plate expressed as the bending stress related to the curvature and a transverse shear stress related to the gradient of the curvature. That's the only information I will keep for now. And note that I've noted chi instead of k, because I don't expect it to be the exact curvature tensor. Okay.
Sorry, exact.
Yes. I mean, it won't be in the end, this guy won't be the geometrically exact curvature tensor, meaning that K was minus U3 alpha beta, okay? In my derivation, this won't be the case anymore. It will be close to that. We'll see this in the end. Maybe. So I need to be a bit faster. So you see that somehow since I chose that the relevant stress localization, I choose to work with the stress localization and not with the displacement localization. I need somehow to express this as function of static variables and not kinematic variables. Okay? Because this is there is no hope this will be compatible and I can apply the minimum of potential energy. In the end, I will have to apply or to use the minimum of complementary energy because I choose to deal with the stress. So I will perform a change of variable. So I recognize that I introduce the bending moment. It's just the bending moment through the I know that I can have the bending moment from the constitutive equation. And since I am dealing with the gradient of the curvature, I will introduce the gradient of the bending moment. Okay? And what I will do is just I will express this approximation of the stress, not as function of the curvature, okay, as originally done, but as function of the bending moment of the gradient of the bending moment. Okay. So there are other ways to derive this, which are less. I understand if you feel a bit uneasy with this way of introducing the bending gradient. There are other ways of doing that which are much clearer. Okay, but I wanted to keep with the asymptotics for introducing Kirchhoff law plate theory. I think it's very interesting also. So let's assume that I can express. I have an approximation of the stress displacement as function of the bending moment and its gradient. Okay, and you see that it's just a matter of substitution. Using the bending constitutive equation, I replace the curvature with that. This is the compliance. Sorry, maybe I haven't said that. Small d is just the inverse of the of capital D. So d is the bending stiffness tensor. So small d is the bending compliance tensor. Okay. So I just substitute chi as function of the bending moment, and I can do the same trick with the gradient. So I have something which writes as function of what will be the static unknowns of my new plate theory. All right? Okay. So I'm happy because if you remember yesterday, I derived the equilibrium equations and I said, I would like to have, if I know an approximation of the local stress as function of the plate variables, I'm done because I can derive the energy. So this is precisely what I do here. So this is the complementary energy, and I inject this approximation of the stress. And if I inject this in the complementary energy, what comes out, I split the integration on the whole body. I split it in integration through the thickness and integration on the plate midplane. Okay. And what comes out that this enables me to derive again the bending stiffness compliance tensor. And this guy will give me new information. Okay, so I retrieve the Kirchhoff law contribution, the Kirchhoff law stress energy density, and I have a new guy which is a sixth order tensor carrying the energy of the gradient of the bending moment. Okay. there is no coupling between the bending moment and the bending gradient, because we assume that the plate is monoclinic. Okay, the local constitutive tensor is monoclinic, so transverse shear are uncoupled with in-plane stress. Okay. So what come out is this sixth order tensor, which is the bending gradient compliance. Okay. So this guy is, you understand why it's a sixth order tensor? I contract a fifth order tensor with a fourth order tensor. I contract twice again with another fifth order tensor, so I get a sixth order tensor. And nobody asked for the notation, but so the bending gradient is a third order tensor with this small parenthesis, and the sixth order tensor I just put twice parentheses. Okay. Just a matter of notation, yes?
Just a question. Yeah, the tensor that you have, they are those that you have deduced previously in the simple... Yes?
Yeah, I mean, I just, maybe this part was not clear, but I just made a change of variable. So you recognize the localization tensor related to the curvature and the localization tensor related to gradient of curvature. I just substitute this because you have this, you inverse this relation between the bending moment and the curvature using the minus d. Yes, they are fully. Oh yeah, that's all the effort was to have those tensors. Sinon, c'est bien la peine de faire tout ça. Okay, so this sixth order tensor is positive. This is clear on the definition. When it comes to clear, it's quite straightforward to see it, but it's not definite, meaning that it can have zeros. All right. So I won't dwell into that. We can discuss that later on because it doesn't make much complication. I mean, but one reason for that, I mean, a simple explanation is that I will retrieve the Reissner-Milling plate theory when the plate is homogeneous. So this means that somehow this tensor must degenerate to retrieve the Reissner-Milling plate theory. Okay, so I have a constitutive equation. I have a stress energy density, and not that the Kirchhoff law of contribution, so the bending contribution is there, and you have the shear contribution, which is properly scaled. Okay, in my stress energy density, which is a plate stress energy density, because it's only defined on it's directly defined on the midplane of the plate. All right. So I'm happy, but if I want to have a plate model, I need equilibrium equations. Yeah. Yesterday we started with equilibrium equation on the blackboard. I derived equilibrium equation very straightforwardly, integrating the 3D equilibrium equation. Now, and I didn't have any. I didn't have the constitutive equation. Now I have what will be a constitutive equation, but I don't have the equilibrium equations. So it's rather pretty simple. I'm just recalling what we did yesterday. So you remember that we have, if you integrate the 3D equilibrium equation, you see that the shear force is the divergence of the bending moment, and that the divergence of the shear force equilibrates the transverse load. Okay? But this is not enough because my new unknown is the total gradient of the bending moment and not the divergence. All right? So instead of using this equation, I will replace this equilibrium equation with this new, I will call an equilibrium equation, which just specify that the bending gradient is the gradient of the bending moment. And I will change the name of this, I said it's a bending gradient, I will call it now the generalized shear force. Okay, it's just an analogy. The shear force is the divergence of the bending moment. I will call this guy the generalized shear force because it generalized this idea. And we will see this is very explicit in the following. It's better to look first at the indices. Q is the divergence of the bending moment. And from the very definition of the generalized shear force, you can retrieve the shear force by taking the trace over the last indices of the generalized shear force. Okay, this is rather straightforward. It turns out that you can write it easily, simply intrinsically, using this tensor, which is just the identity for in-plane elasticity. I think you know this guy, and you contract 3 times with the generalized shear force, and you retrieve the divergence of the bending moment. So you retrieve shear forces. So, namely, this equation really generalizes this one because I can project this equation with I. Okay, I contract 3 times with I this equation and retrieve this equation. Okay, this is why it's the generalized shear force. So why doing that? So I just write explicitly the link between the shear force and the bending moment here. Okay, so we have Q1, it's M11, 1, M12, 2, and Q2, which is M211 or 121, and M plus M22, 2. And this is, I make explicit reference to the the generalized shear force. Why do we need this generalized shear force? Because in the stress distribution related to shear, we need to make distinction between the components, these components of the bending, the gradient of the bending moment, and this one. Those components, each component of the bending moment, of the gradient of the bending moment, generates different local fields, different localization. Okay? So this is why I need to make distinction between all components of the gradient of the bending moment instead of taking only its trace, namely its divergence. Okay, and I need to make this distinction to have a precise description of fields in the plate. All right. So I have this, and to summarize, this will be my statically compatible fields. So the transverse shear, the transverse equilibrium, and the generalized bending equilibrium. Okay, and this is, you recognize the shear forces, and this is the with indices. So I have the energy. I have the stress energy. I have equilibrium equation. Okay. So I have a plate theory. Okay. The only thing in which I want to say is that you must notice that this, if you take the 3D equilibrium, you inject this in the 3D equilibrium equation, this is not a completely statically admissible field in terms of 3D. Okay? It satisfies the 3D equilibrium equation at a higher order than Kirchhoff-Love stress distribution. Okay? Actually, you can go higher, and we were able to derive a fully statically, completely statically compatible stress distribution, but it's much more complicated and it's not very practical. Okay, and it doesn't change the result I will present here. Anyway, so what will follow is just exactly the same thing we did yesterday with on the blackboard, but with those new variables. Okay. So I will introduce the generalized strain, so the curvature, which is not exactly the curvature in the sense of Kirchhoff, as the derivative of the stress energy with respect to the bending moment, and the generalized shear strain as the derivative of the stress energy with respect to the generalized shear force. Okay? Yes, I haven't mentioned that, but it's pretty obvious that the generalized shear force is symmetric with the first indices because the bending moment is symmetric with the first indices.
Just for joking.
Yes?
Are you sure that Lebe-Schmidt notation is worse? Look at your phone.
We can discuss that later. If you have suggestions.
I think it's Lebe-Schmidt.
Well, but I'm not sure what you mean exactly by Lebe-Schmidt notations.
In the index notation.
Keep this one and don't look at that. That's it. What do you mean? I understand you. But when I have 6 order tensor and for the totally statically admissible plate theory, I have 8 order tensors.
Double theory that 3 dots
Yes.
are dot.
Yes. I agree with you. Is that notations? It's always a problem. But yeah, I tell you, I have in more general models, I have 8 order tensors. It's just ugly. I don't have the old Greek alphabet is not enough. I mean, if I do 3 contractions with 8 order tensor, with
Okay, we'll talk about it.
it's a long story. But I understand your remark. So if you do that, you just compute the derivative of the stress energy. You find directly the constitutive equation, namely that what I started with, the curvature is related to the bending moment with the bending compliance, okay? And this is straightforward. And you can see that the generalized shear strain is proportional to the generalized shear force. So with indices, this is starting to be a bit cumbersome. Yes?
Do not have any full plane to assume.
Monoclinic symmetry. I said that. I mean, when I computed the energy, you don't have coupling between those guys because transverse shear are uncoupled from in-plane stress and Poisson effect because of monoclinic symmetry. So we have the constitutive equation, and now I take the equilibrium equation and I take their weak form, and I will find the principle of virtual work in the end. So I do it with Levi-Civita's notation. So what I introduce with the very new thing, or let's start with the classical thing. This is the divergence of the shear force, okay, and you just multiply with what will be the out-of-plane displacement as the Lagrange multiplier of this equilibrium equation. So this is rather classical. But of course with this third order tensorial equation, I need to introduce a third order tensor Lagrange multiplier. And this will be our generalized rotation. Remember, yesterday we had the rotation. I mean, Meissner's rotation came out from the we had this relation, and I multiplied. This is a dot with phi. Okay, this was a kind of something which was related to the rotation, which is the slope of the plate, or the slope of the normal fiber. So now the generalization of this equation is this one with this generalized rotation. So I don't think I will have time to dwell too much on the mechanical meaning of this guy, but I can give you more details. I mean, it's pretty clear. There is not so much difficulty. All right, so I'm just combining, summing those equations, doing the classical machinery of principle of virtual work. I sum the relations. This is with full initial notations. Okay, I have the internal power of the bending moment times the curvature, what will become the curvature. I have the power of the generalized shear force contracted with what will be the generalized shear strain. I have the work of the external force, and I have the work on the boundary. Okay, I don't know which one is better. This is the same thing with intrinsic notation. Okay, I find it more easy to read, but it's not obvious for everybody. I understand that. All right. Okay. So we identify the power of the internal power, and the work of is the external work. Okay. So it's exactly the same story. It's a bit too much detailed, and we find that the curvature is the divergence of the third order tensor. Live with it, and the generalized shear strain is the sum of it's actually somehow the difference between the generalized rotation and this guy which looks nasty. But if I recall you, yesterday we derived shear strain, we had chi. I will use indices notation. We had the curvature was phi alpha symmetrized. Okay? This was the Reissner's curvature. Okay? Then we had the shear strain, which wrote the difference between the slope and the slope of the midplane and the slope of the normal fiber. Okay? So this is really easy to understand. It means that my plate is deformed that way, and the normal fiber rotates by itself with its own freedom, and this is minus phi alpha, this is U3 alpha, and this is gamma alpha. Alright? So the difference between the inclination of the normal fiber and the actual slope. So this is just the generalization of this idea. Alright? And we have the clamped boundary conditions. I think it's more instructive to look at the work on the boundary. Okay, this is on the boundary. You see that if you want to have a clamped boundary condition, you must vanish this guy and vanish U3. Okay. On the static side, this is really exactly as with Reissner mainly, because you recognize the shear force with Q dot n, so it's the out of plane force on the boundary. And here you need to vanish all components of the bending moment, because there is an additional boundary condition with the bending gradient theory. Again, I think I don't have time to go into details, but I can give you explanation for that. So if I gather all the equations, I had the equilibrium equation we discussed earlier. I found the constitutive equations, and I have those compatibility conditions and the following clamped boundary conditions. Now you can inject the definition, you can isolate phi from the definition of the generalized shear strain and inject in this equation, in the definition of the curvature. If you do that, you can see that the curvature is split into an exact curvature plus a small correction related to the generalized shear. Okay? So obviously, if you set eta to 0, you end up exactly with Kirchhoff love plate theory. Alright? That's why I said this new curvature won't be exactly the geometric curvature of the plate. Alright. And I will finish with that. Okay. So now that we have this new plate theory, which is a bit involved, okay, and I try to use to be as close as possible as the way of, the original Reissner plate theory with new tensors, a more complicated tensor, but the formalism is as close as possible as Reissner formalism. I know the stress localization because it's the starting point. So I know the local 3D stress distribution quite precisely. I need the displacement distribution. Actually, you can use what we obtained from the asymptotic expansion. Okay? So I can say, let's define this approximation of the actual 3D solution. And I just plug the deflection and the gradient of the deflection of the bending gradient theory, and for the higher orders I use the curvature of the bending gradient theory and its gradient. And if I do that, I can compare the strain related to this displacement localization to the strain related to the bending gradient stress. So I can compute another estimation of the strain directly from the stress, and you can check that the compatibility is satisfied up to a higher order in terms of the small parameter. Okay, so you can estimate here the how much you do not satisfy the compatibility equation. All right. Okay. And I think it's 10 after 5. I think it's the right moment for making a pause, and so I suggest that we gather at 40. That's okay. That's We made a long path in order to derive this very tedious, terrible plate theory involving the gradient of the bending moment, so which is the generalized shear force. Actually, I will show now that this complicated plate theory is just turned into the original Reissner plate theory when the plate is actually homogeneous. Okay? And the very reason, I mean, there are several ways of understanding that, but one reason is that I say that the transverse shear compliance tensor, this guy, H, is not, it's positive, but not always definite, positive definite, so it has some zero. What I haven't mentioned is that the generalized shear force has 6 static components, okay? Whereas the shear force has 2 components, it's a vector. This is a third order tensor, which is symmetric with respect to the first indices, so it has 6 independent components, okay? So in Voigt notation, this is a 6 by 6 matrix, and it may be rank 6, but it can degenerate up to rank 2. Okay? And this is the case when the plate is homogeneous. So I will rederive Reissner-Millin theory when the plate is homogeneous. So I just specify the stress distribution we derived from asymptotic expansion, okay? But as I specify it in the case when the plate is homogeneous. So let me remind you that I had Sk, which was Z times C sigma alpha beta gamma delta. It's a fourth order tensor, okay? Alright? And to have the stress localization as function of the bending moment, I multiplied with the bending compliance. Okay? This is what I did. Okay? And it turns out that when the plate is homogeneous, this is constant. You can compute the bending stiffness, which was defined as follows. Okay? And it's just, you can factor out the plane stress stiffness tensor. So it's just 1/12 of C sigma. Okay? And of course, this is the inverse of this guy. So this is 12 times the inverse of this one. So the inverse of this one contracts with this one. So in the end, you have the identity. All right? So this very specific simplification occurs for homogeneous plates and some specific cases. I will show that for sandwich panels it's the same situation. This occurs also for functionally graded materials. So there are many situations where this can occur, okay? And hopefully there are situations that this does not occur and we need the bending gradient theory, okay? Otherwise it's just losing my time. But this is what I write here. So the in-plane stress, which is related to the bending, actually is directly proportional to the bending moment. It's 12Z times the bending moment. Okay? I forgot 12. All right? And the transverse shear strain, it's the same trick, but here you see that the identity tensor is contracted 3 times with the generalized shear force, and actually it is the shear force. Okay? And the out-of-plane tensor is 0 in here. And this is the stress distribution used by Reisner for deriving his plate theory. Okay? So this is the you can express directly instead of you don't need to keep all the 6 components of the bending gradient of the generalized shear force. You can keep only the 2 components of the shear force as which carries the energy related to shear. All right.
Just a question.
Yes.
This will be also what you get with homogenization, also this distribution or not?
Yes. You will get this as directly the stress will be directly function of the shear force, but the displacement localization related to the shear, the transverse shear of warpings, it's not only the shear force. It's a bit subtle. All right. So this this is why you retrieve Reisner mean. And if you inject this this inside the whole machinery of the bending gradient, you see that we have the transverse shear energy, which right this way. Basically, H becomes this way, rise this way because I can factor out this the identity tensor. Remember, I have this identity tensor, and I will compute the energy. So H used to be transpose S R okay. Now I can inject this distribution. I will say that this may be written SR writes F of Z times I. Okay. Sorry. I can write the transverse shear strain localization tensor as alpha 3 gamma delta beta gamma delta as Fz times I alpha beta gamma delta and S alpha gamma delta epsilon, as well as so. I want to be precise. So if you remember, okay, sorry. The only in order to derive the transverse shear compliance tensor, which is a 6th order tensor, I need to compute that, and I want to specify that, and it turns out the only non-zero component of this tensor are the transverse shear components, which may be factored out with a function of z times the identity tensor. Okay, if I compute that, what I get is okay, times, and this is what is here. Okay, so alpha 3. And I will have delta epsilon theta theta. Okay. All right. I hope it's clear. You have this the identity tensor factors out, and you have only an integral on a 2nd order tensor, which will be HRM. Okay, this is HRM, which is the compliance Reisner-Millin compliance tensor. Okay, and actually, when it's homogeneous, you retrieve exactly so it's a compliance. So say 6/5. So the 5/6 shear correction factor, which is quite well known with Reisner theory. Okay. Okay, and this very specific form for the bending compliance, the shear compliance tensor, makes that you can write the energy this way. Instead of the generalized shear force, you just need the conventional shear force. Okay. And if you specify now the constitutive, you use the constitutive equation. The original, the bending gradient constitutive equation, you can see that it simplifies in the following way, because you have you contract 3 times with R, so you see you have the shear force, and you can see that you can factor out this identity tensor and retrieve the Reisner shear strain. Okay, and this is the Reisner mean-link constitutive equation. Now this is the kinematic compatibility equation. You see straightforwardly, since you can factor out the identity tensor from gamma, you see that you can write the generalized rotation the following way. You can factor out this identity tensor, and if you inject this inside the compatibility equation of the bending gradient, you retrieve exactly the Reisner mean-line compatibility conditions, and you retrieve also the boundary conditions. So in the end, we have the Reisner, we retrieve the Reisner mean-line plate theory when the plate is homogeneous. And this is the very reason is just this factorization, this very simple factorization of the stress localization, the bending stress localization tensor. Alright, so I'm done, and from this helps us to define the distance between the bending gradient and the Reisner mean-line models. So a way, I say a way because the projection is not unique. A way of deriving a Reisner mean-line plate energy instead of a bending gradient energy is noticing that you know that we have Q is I contracted 3 times contracted with the generalized shear force. Okay, I explained the origin of that is just to take the trace of the gradient and you get the divergence. Now we have the following property. If I you have the following property that if you contract 3 times the identity with itself multiplied by 2/3, you get the identity of second order tensors. Okay, this is Kronecker symbol. So actually, this is this relation allows me to write to build a projector for the bending gradient. How I will do that? This allows me to introduce, let's call it P Reisner. I define this 6th order tensor as, so just one contraction, and if I compute PRM with itself, I contract it with itself 3 times. Okay, you see that this contracted 3 times with itself. You use this interesting property, and you find out that it is a projector. Okay. So so now I have this projector. So if I compute such that, I have a projection operator in order to turn the bending gradient, the generalized shear force into the conventional shear force. So if I use this projection, I can project on each side of the generalized the shear compliance tensor, and this will give me the Reissner-Millin equivalent of the bending gradient model I am considering. And if I make the difference between the original tensor and its projection, I get the pure warping contribution of the bending gradient. I try to explain it. It's a bit difficult. And if I compute the norm of this estimate of the warping contribution in the bending gradient and the relative difference between this warping contribution with the total contribution in the sense of this norm, I have an estimate of the non-Reissner-Millin contribution in my shear compliance tensor. Okay? So if I compute this for several laminates, so in the following I will consider laminates made of carbon fibers reinforced polymers. So each layer has one direction with different orientation. Okay, and if I have only one orientation, so it's homogeneous, I get the Reissner-Millin plate theory. But if I have 4 layers, so I'm not sure if you are familiar, this is the orientation of the layer. So this is 30 degrees, minus 30 degrees, and if you have this S, it's the symmetric lamination. So it's 4 layers, and this is an 8 layers laminate. You can see that the estimate of the difference between the Reissner-Millin and the bending gradient theory is getting a bit large. It's 16%. I think it's not very large, in my opinion. And so you cannot say that laminated plates are Reissner-Millin plates. Okay, they are bending gradient plates. And the last example I will show, it's this figure, this distance is almost 90%. Okay, I have a situation which is very strongly not a Reissner-Millin plate model. Alright, so this is for the distance between the bending gradient and the Reissner-Millin plate model. Now I will show illustration with laminated plates. So I briefly, I briefly introduced void notations, but I don't think it's really critical or very interesting. But I use symmetric void notation with respect to the bending moment and the curvature. So you have the square root of 2. This is convenient in the present situation. Okay, it's much more convenient than the classical, the engineering one. So this is for the bending moment and the curvature, and you have the following 6x6 matrix for the 6th order tensor with the following ordering of the components of the bending gradient. It turns out that it's not the same as Nicola, the one of Nicola, but anyway. And with this void notation, it's quite easy to handle calculation. And I will illustrate this with the cylindrical bending of laminates. Okay? So, this is a kind of inevitable exercise in the laminated composites community. You must compare with the exact solution derived by Agonal in the 70s, almost 70s, for the cylindrical bending of laminated plate. Okay? It's almost an academic exercise now. So Agonal derived an exact solution for the bending for the bending of laminates with the following boundary conditions. The following boundary problem. You have a laminate. It is symmetrically laminated, but he considered a non-symmetric either situation. You assume that it is infinite in the direction 2. Okay. It is loaded on its upper and lower face with a sine shape, sinus distribution with respect to the direction 1. Okay. And it shows very peculiar boundary conditions, assuming that the out-of-plane displacement vanish on the support. That's why I've drawn those fancy boundary conditions, but it is a 3D solution, so it's a 3D boundary condition. Okay, and he assumed that what we call in engineering simple support, soft simple support boundary condition, meaning that the normal stress and the tangent stress is vanish on the boundary. Actually, implicitly, it's just a Fourier. It's kind of Fourier decomposition, or you are considering plane waves for the laminate. Okay, but it has an engineering meaning. And if you do that, you can perform a variable separation and solve analytically the 3D problem, and you have hyperbolic functions through the thickness and sine functions in plane. Okay, this solution has a very specific features, and that's why it's a closed form solution. There is no boundary layer because it's not clamped. It's a simple support, so no boundary layer. It's important because after I will compute some convergence estimates, and this point is critical. Okay. All right. So this is for Pagano's boundary value problem for the cylindrical bending of laminate, and you can solve this the same problem for bending gradient plate. I won't detail the calculation. I mean, it's rather straightforward. It's a second order differential equation. I mean, unless you want it, but all right. It's pretty simple, and this allows me to derive the local stress inside the plate at specific position, and the local 3D displacement in the plate. Okay. So I will first show the stress localization tensor. So the three graphs at the top are the in-plane stress. So sigma 1,1, sigma 2,2, and sigma 1,2. Those sigma 1,1 and sigma 2,2 are taken at midspan of the plate. Okay. Sigma 1,2 is taken at the boundary, at the support of the plate, and those two are the transverse shear. They are taken at the boundary, on the edge. This is the position where the shear force is maximum. Okay, and this is the normal stress of the plate. Be careful. I carefully normalized those stress distribution with respect to so that it becomes on the graph of the same order of magnitude. Okay, but those are supposed to be getting small compared to those because of the scaling of the plate. And look, I plot the distribution for the exact solution, which are the most distorted ones. Okay, it's black, but the colors are not very nice on this screen. I plot the bending gradient solution in green. Okay, and I plot the Kirchhoff solution in blue. Okay, so they are not exactly the same for the bending stress. Okay, and for the transverse shear stress, there is no Kirchhoff law of localization because it doesn't come out in Kirchhoff plate theory. Okay, so here you only see the comparison between the exact solution and the bending gradient solution. Okay, and of course there is no out of plane stress in the bending gradient theory, so its both are zero, but I still plot the exact solution, which is not zero. All right. And okay, you might say, okay, it's just ugly, but look, the slenderness, the thickness is the same as the span. All right? It's already pretty good for such horrible. I mean, it's not slender, right? So if I go higher in the slenderness, 139, 2, almost 3, almost 4. 6. My eyes are starting almost not making difference between the exact solution, and it converged very fast. This is 20, the slenderness, and the curves are matching. Okay. And now this is for the displacements. This is U1s with the in-plane displacement taken at the boundary This is due to the in-plane displacement in the infinite direction taken at the boundary, and this is the global deflection at midspan, U3, normalized with the exact solution because it goes very far because of the scalings. Okay, and you see the exact solution, the bending gradient approximation, and here the Kirchhoff love approximation. Again, we start with slenderness 1. Okay, so this is not very surprising that Kirchhoff love is very, very poor in this situation. Okay, and if I go, I make the plate slender. It is converging, and you see that Kirchhoff love is painfully trying to reach the exact solution, and even at 20 we are not very good. Okay, once the model is converged, it's interesting to see that okay, the bending gradient is almost collapsed with the exact deflection. For the in U1 direction, you see that Kirchhoff assumption is pretty good. Okay, but when the plate is not slender, it's not true. Okay, so this is the shear warpings which we derived with the asymptotic expansion. That's where they are coming out. And once the plate is converged, the normal is getting straight with respect to it follows the slope, and it's almost straight. Okay, and this is a higher order contribution. It's not scaled the same way. So this is just a warping in the infinite direction because of the couplings. All right. So I do the same presentation with a more complicated stack. It's a 9-layer. Okay, it's still symmetric. You see that we have complicated distribution, and this is why it makes so. You have such a large literature about laminated plate theories, because capturing those effects. Everybody noticed that the Agonal solution is very, very complicated, and we need large enrichment of plate theories. Plate theories with many enrichments. All right, and this is the same for the transverse shear stress. So you see that it's nicely converged with the exact solution. And again, this is for the displacements. This is the same story. I kept this example because you can see that here this warping distribution is zigzagging. Okay, and there are many plate theories introduce some zigzag functions to capture this effect. But it's just the fact that because of the different orientation of the layers, some components of the stiffness tensor are just alternating, and you integrate them through the thickness, and you get those oscillations. Okay, that's nothing more. All right. So this is an illustration for the for laminates. Okay. So convergence. I won't pretend. We never tried to prove any higher order convergence with the bending gradient plate theory. We know that anyway it won't converge faster in terms of convergence rate, but I show you empirical convergence diagrams. Okay? So the deflection error is you take the plate deflection for the Kirchhoff love and the bending gradient plate theories. And you compute the difference between the average through the thickness of a Agonal solution, so the exact solution. And the stress error is just the L2 stress error in the sense of the stiffness energy, stress energy, in the sense of stress energy. Okay, and you have the slenderness, and you can see that Kirchhoff love is for slenderness 10 is pretty poor because it's more than 10% error. It's log scale, and you see that the slope of this convergence is t square or eta square. Okay, the smallest parameter square, and you see that the bending gradient converge at the same rate. Okay, so it doesn't converge faster in terms of deflection. But notice that the difference between the two curves is 2 orders of magnitudes. So even if it doesn't converge faster, it's 100 times more accurate than the Kirchhoff law of plate theory. Okay, so I would say that asymptotics are nice, but seeking for higher order or higher convergence rates does not always make sense, especially in terms of practical applications, because we don't deal with actually slender structures. Okay, and here precisely, I don't pretend that it converges faster. Actually, it does not, but it is it's much more interesting to use the bending gradient theory compared to Kirchhoff law of plate theory in that case. Okay. This high convergence rate is observed because we don't have any boundary layer. The plate is not clamped. It is simply supported. And you have convergency, I didn't say that previously, but for Kirchhoff law of plate theory, there are convergency results which were well established. And it is established that when the plate is simply supported, you have this convergence rate. And when it is clamped, you don't have t squared, you have t to the 1/2. It is a very, very poor convergence rate. Okay, and actually, if you don't enrich the problem or make asymptotic, or you don't match asymptotics on the boundary and in the inner solution, you will never improve this convergence rate. So there is no hope. So that's like unless you have some fancy, it's much more complicated. So this is a convergence result which is so this is consistent with the convergence for Kirchhoff law, and the bending gradient is just better, but follows the same rate. In terms of stress error, you see that you have the the slope is 1 for the Kirchhoff law stress distribution, and for the bending gradient stress distribution, you have a higher convergence rate, which is t squared. Okay, and this is the expected convergence rate for the Kirchhoff law plate theory. All right, so it's a better approximation. So this is for empirical convergence diagrams. It's not a convergence result, but it's quite interesting anyway. So now periodic plates. All right. I will be much faster, and this hides many difficulties actually, because periodic plates are there are some subtleties. But okay, the purpose of this section is to extend the bending gradient to periodic plates, and I will give very briefly an illustration with sandwich panels and an illustration with a beam lattice, and which is interesting because it's absolutely not a Reissner plate, thick plate. Extension to periodic plates. What is a periodic plate? It's just the plate. You have a RVE, which is periodically reproduced in the plane of the plate, and of course the upper and lower face of the plate are free. Okay, it's a plate. Otherwise, it would be a 3D medium. So the periodicity is in the plane. Okay. You have the same boundary value problem, and I evacuate philosophical question of how do you actually apply the boundary condition on this stuff. Okay, it's just suddenly, with laminated plates, the 3D problem was clearly defined. There were no problem, and the variable separation is completely established. We just rescaled the out-of-plane coordinates with respect to in-plane coordinates. There is no cheating. Okay. Here it's much more complicated because you cannot really be sure of the position you put the boundary condition on the plate. Where do you put the plate? It's not very clear. If you clamp that, where do you clamp? Okay. So there are philosophical problems with that. Anyway, formally, it is extremely similar to what I presented. You can perform an asymptotic expansion and do exactly the same developments I've presented. Okay, but the only difference is that instead of separating the out-of-plane coordinate to the in-plane coordinates, you will have at the microscopic level the in-plane coordinates, but at the so at the macroscopic level, the in-plane coordinates, and at the microscopic level, the RVE, so 3D coordinates. Okay? So those who are familiar with 3D homogenization is exactly the same framework. Okay? And you can perform the asymptotic expansion exactly the same way as for 3D periodic media. All right. Here you could argue what is the small parameter. We will say that the thickness of the RVE is quite the same as its width. So when I go to the limit, all those dimensions goes to 0 at the same rate. Okay. But there are people, there are derivations where you can, change the rate, the convergence, the scalings of those dimensions. I consider the situation here where everything is scaling the same, zooming the same at the same rate. So if you do all the same machinery we did for the laminated case, formally you end up with the first significant auxiliary problem. It is exactly the same as for the bending of the laminates, but here, instead of having something you need to integrate to the thickness, and we did it analytically, here you need to solve an auxiliary problem on a RVE. And this auxiliary problem tells you just apply on average a curvature on the RVE. Just curve the RVE or torque the RVE on average and assume periodic boundary conditions. Okay, so it's not very conceptually, it's exactly the same. It's just the fact that you have a 3D RVE instead of a line which you integrate through the thickness. All right, and if you solve this bending auxiliary problem, you will find localization tensor related to the bending, so bending stress, but it's a 3D stress. It's not purely in plane now. This was done by Kairi some time ago, and I think he proved the convergence result on that because these procedures lead to the Kirchhoff plate model, and so you can homogenize the periodic plates at the Kirchhoff plate. But we want to get the effect of transverse shear, or the effects of the generalized shear force. So you can, doing the same kind of machinery, you can derive a shear auxiliary problem, which you have to solve, which is, here I directly parameterize this auxiliary problem as function of the generalized shear force. But it's, I already, okay, and this, solving this auxiliary problem will give you the shear compliance tensor and the localization related to the generalized shear force. Okay? So this is, basically, you extend everything I said, but you take it on average on the RV. Okay? But it's a long story, but formally, it's exactly the same situation. So now I will investigate the case of sandwich panels, and this application where this is the origin of the motivation of all this work. So I will consider my RVE, and I will divide it in 3 pieces: one skin, one lower skin, one upper skin, and a core between those skins. Okay. And I apply the bending auxiliary problem on this RVE, for which I have specified I made those specifications. If you assume that the core area is very compliant, okay, you can say that only the skins contribute to the bending energy, okay? And this is what is classically done in sandwich theory. But the advantage here is that since we used the correct bending auxiliary problem, we can quantify precisely this contrast assumption. It is very often a bit fuzzy in the literature. What is the correct contrast assumption? If I assume that my faces are made of the skins are made of the same material for the cores on the skins, and that my core is a cellular core made of facets of thickness TF, my contrast assumptions tells me that I must have the facets much thinner than the skins. Okay? It's quite the situation with honeycomb sandwich panels where you have very thin foils for the honeycomb core compared to the skins. Alright? So this is very intuitive, and it's in accordance with the engineer's calculation. And now what is interesting is that if you consider the the shear auxiliary problem, the generalized shear force auxiliary problem, it turns out that exactly as with homogeneous plates, the bending gradient theory is turned into a Reissner-Milling plate theory. Okay? Namely, this shear auxiliary problem is function only of the shear force and not all components of the bending gradient. You can show that. Okay? That's the first result. It's nice because Reissner-Milling plate is easier. It's in every code. So instead of you don't have to implement specific finite elements. And the loading you must apply to the RVE is very intuitive. The loading is just tells you that you take the skins of you take your RVE of the sandwich panel, and you must load the skins with horizontal loads, okay, and which put into shear the core. So it's very intuitive and corresponds to what is used in sandwich theory for deriving empirical plate models. Okay, so it confirms the classical intuition of the fact that shear forces put into shear the core through the skins. You load the skins and you put into shear the core. All right, so let's apply that to a sandwich panel. So that was the starting of my PhD thesis. You recognize, for those who are familiar with origami, a famous origami which is called Mura Ori, or chevron pattern. It has several names. And you can use this as a core of a sandwich panel. Okay, there were many investigations on patents and fabrication process for this core. The advantage is that if you can produce it just by folding. So compared to honeycomb, when you have to glue alternatively some foils of aluminum to expand it and so on, blah blah blah. This seems much simpler to produce. Actually, it's quite difficult to produce. Okay, because you must not stretch the foil, and it's not so obvious. All right. So I will use this pattern, this core, this fold as a core for my sandwich panel. And if I do that, I show you first the bending computation on the RVE. Okay? So you recognize here in orange the skins, the upper skin, the lower skin, and this is the fold, okay, in blue, mostly blue. This is this guy, okay, but just a unit cell of this guy, a bit more folded. And what you see is the numerical confirmation of what I just said, is that when you bend the RVE, the skins are mostly put into traction, okay, traction and compression, and the core is not loaded actually. And this is von Mises. Von Mises in the sense of place in abacus, okay, so something which is a bit weird, but anyway. And you have here the bending in direction 1, tie 1, so direction 1. So I bend, the curvature goes in this direction. Here it's bending in the other direction, so the curvature is going that way. And this is the torsion loading. Okay, you see that the skins are put into torsion. Okay, but the main observation is that the core is not loaded. Okay, it's only the skins, and this is why it is turned into Reissner. So this is quite classical. I mean, it's just application of Cayley's homogenization scheme. Now, if I go to what interests me is the shear forces, the effect of shear forces, because I know now that it's a Reissner-Milling plate, so it's shear forces which act on my RVE. And I see that I have two computations to perform. And what occurs is that you observe the relative displacement of the lower skin with respect to the upper skin. I put my fixed point here, so the lower skin is just going backside. Okay, so this is shearing the RVE in Q1 in X1 direction, and the same for Q2. Okay. So this homogenization scheme gives something which is very conform to the intuition of the engineer. And the fancy thing is that it turns out that with this very specific core, you not only have this relative displacement of the skins, okay, corresponding to overall shearing, but you have also out-of-plane displacement of the skins. Skins distortion, I call it. Okay, this is because of the very specific shape of the core. This does not occur much with honeycomb cores. Okay, and it turns out that it explains that we could not estimate properly with conventional methods the shear force stiffness, the stiffness related to shear forces. Okay, but I won't go into details in this graph, but it provides us a very accurate estimate of the shear force. We validated the estimate with the full 3D calculations. Okay, this is for sandwich panels. And I will talk, and this is the last example, so I'm a bit shorter, but it's okay. Why all plates are not Reissner-like. Alright? So for this, I will homogenize an orthogonal beam lattice. So I consider this grid, and I assume that macroscopically I want a thick plate model, so a bending gradient plate model. And microscopically, this is just two Saint-Venant beams. So I consider those pieces as beams. Okay? And this will be my microstructure. Okay? So this is my RVE. I have two beams corresponding to those two beams. And if I reproduce periodically those beams, I get this beam lattice, this orthogonal beam lattice. Alright? I want to homogenize that. If you forget about those bending gradient theory stuff, if you are someone who wants practically to know what is the effect of shear forces in that stuff, how do you do? Do you have any idea? Well, actually, what is the definition of shear force here? The definition of bending is not really clear either. Well, it's not, in my opinion, it's not very obvious. Okay? There is a second reason, so it's solving this problem, having a thick plate model for that is not obvious. The second reason is that you see that this pattern follows cubic symmetry, meaning that if I rotate from pi for 90 degrees my plate, you don't see the difference. Okay? And it turns out that if I want to model this plate with a Reissner plate model, since it is orthotropic, okay, and I have this pi/2 rotation, I will have a bending constitutive equation which is orthotropic and cubic, but the shear force stiffness tensor, which relates the shear force to the shear strain, it's a single order tensor, and those symmetries are just enough to have an isotropic constitutive equation for the shear. Okay? But obviously, this is not isotropic for higher order effects. There is no reason for this to be independent. That shear forces are independent of the orientation. Okay? So, I rephrase this. This is the Reissner bending constitutive equation. This is a 2x2 matrix. Since I have orthotropic symmetry, meaning I have two vertical planes of symmetry, and the pattern is invariant by a rotation of 90 degrees, this tensor must be isotropic, meaning I have some constant times the identity. So basically, if I shear this stuff in one direction, it's independent of the direction of shearing. But obviously, if you shear in this along a beam, it's not the same if you shear along a diagonal direction. All right? No? That's why it's a good example. you try to. So I have this thing. So let's say that I consider Q scalar n, okay, is the vertical force for, so this is my plane, I take a normal in the plane of the plate, and Q scalar n is the vertical force along this line. This is the definition of the shear force. Okay? So let's assume that you have this normal. Intuitively you say, my shear force, my average shear force is just the average of the shear force in each beam, which is true. The same in the other direction. Now, if I do that, say cut this way, and you shear that out of plane, what happens? Yes, but it's not enough. That's true. There's a good intuition, obviously, but you are missing something. This is precisely what the bending gradient captures. So I will just explicit what I just said. So when you want to homogenize this plate as a thick plate, you first compute the thin plate constitutive equation, the bending constitutive equation, and I will present the what happens inside the RVE. So inside the RVE, you have two beams, okay, for each direction. And obviously, those beams have their own resultants along the line, namely, the resultant and a bending moment and torque. So longitudinal force, shear forces, two bending moments, and a torque. A torsion. Sorry, I'm not sure, always mixing. For each beam. Okay? And what we want to know, basically homogenizing this, is to know the effect of a global bending moment inside the RVE. Okay? And the effect of the global bending is that the resultants along the lines, along the beams, are zero, and you put into bending the beams. So my notation is that small r, vector r, is the resultant along beam 1, r1, beam 1, r2, beam 2, and this is the resultant along the beam generated by the bending moment. And m, vector m, is the moment vector along the beam. Okay, so this is torque. This is bending in direction along direction 2, and this is a couple along direction 2, and this is the out of plane couple, and there is no out of plane couple for the beams. Okay, no drilling effects, for instance. You see that if I bend my plate in direction 1, so I want to bend, so I apply a bending moment along direction 2, but this is M11. Basically, this bends those beams. This is what is written here and represented here. Locally, if I bend my global plate with M11, I bend only this beam along this direction. Alright? Exactly the same thing occurs for the other beam when you bend the plate in this direction. Okay? So along -1. Okay? This is the effect of M22. Okay? You bend this beam. Okay, those beams. Now the effect of the torque, the torsion moment, is actually you put both beams into torsion. It is very close to the intuition of what is torsion in this situation. If you put the plate into torsion, you generate torques inside the beams. So it's a good explanation, illustration of what is torsion in plates. All right? So this is for the bending, so the leading order, the thin plate model. And now what occurs if I look at the effect of the bending gradient? So now I have the localization as function, I had the one as function of the bending moment. I have the localization inside the beams as function of the gradient of the bending moment, the generalized shear force. Now I have resultants along beams. I have out of plane resultants, and what I see is that you can retrieve, actually your intuition was exact, meaning that if you put you shear in direction 1, you will shear the individual beam in direction 1, and the same in direction 2. But of course, this is you see it as a combination, as a linear combination of the right component of the bending gradient. Okay. And what you were missing is that, you have additional torques, bending and torsion inside the beam, which are related to individual components of the gradient of the torsion. R1 to 1 is the gradient of the torsion with respect to one direction. R1 to 2 is the variation of the torsion with respect to two directions. On those variations, it generates torque inside the beams. So if I recall, if I bend in direction 1, I bend this. If I bend in direction 2, I bend this one. If I put into torsion, I torque both beams. And now, if I make the gradient varying, okay, I will put into shear individually each beam. So you will have shear force in each beam, which corresponds to the intuition, but also a non-uniform torsion inside the beams. And it turns out that the elastic energy carried by those are much larger than those. Okay, so it means this is directly related to shear forces, and these are indirectly related to shear forces, and they carry a lot of energy. Okay, this is why when you compute the shear energy of this beam lattice, and you compute the distance between the Reissner-Milling plate theory and the bending gradient plate theory, you can go up easily to up to 90%, which is purely bending gradient. Okay? And the Reissner-Milling is just 10% of the shear energy. Alright, and okay, this is just a short illustration, but it is you can do the same trick. I mean, perform a cylindrical bending of your beam lattice. Okay, and I compute also an exact solution for the beam lattice. It's a bit cumbersome, but you can do that. Okay, with classical beam theory, and I can make the comparison. And what I present, it's half a span. Okay, and I'm looking at the bending moment in the beams and the torsion in the beams. Okay, and I'm following this red path. So I'm following all beams which are plus 45 degrees along the path. So I'm going from there to there, and then from there to there, and then from there to there. Okay, and this is plotted in there. And what you see is that if you use Kirchhoff law of approximation, you have the red curve for the estimate of the bending moment, the local bending moment inside the beams. Okay, and the same for the normalized torsion. So you have this sine shape distribution. Whereas you have the exact and the bending gradient, which fits very closely together, and you can see this jigsaw pattern on this stair pattern. Okay, and which is related to those higher order effects and the variation of the bending, related to the bending gradient contributions. Okay, and typically you can see that you have an inversion of the moment in the beam at close to the support. Okay, this is the support, and this is the midspan. Okay, I'm not sure if this is the most clear way of showing that. And you have discontinuities, which is normal because you have knots here. So you have, it's normal that you have the discontinuities of those fields. All right. So this is it for. This is the references. Yeah. So this is it for my presentation. And if you have any questions, late in the afternoon.
just a curiosity. How you, for the plate that you fold, you know how you can fold it or not?
Yes, I can fold it right away.
Can you...
You want a teaching?
Demonstration or?
Oui, bien sûr.
It's very interesting, even for the mechanical point of view.
Bien sûr, c'est tout à fait. So, you take a piece of paper. I can give you some if you want, but if some of you want to fold, no, I will do a demonstration. I can show you how you can fold that. Bon, je vais garder ça pour pas vraiment très passionnant. Vas-y, prends une feuille. If someone wants a sheet of paper. Alors. Actually, it's completely not a machining. I mean, it's the folding process for human is not the same for machines. Okay. So what you first do is accordion. So you first fold your sheet in two. Okay. You don't need to be very accurate. All right. Then you fold again twice in this direction. All right. I think you end up with here. You will end up with 4 strips. All right. I think we can do it with 4 strips, but you can do as many as you want. Okay, it's periodic pattern. But if you so you're done. Okay. So now what you do is you fold all layers all together. First in this, first one in this. Okay. With a whatever angle, but you can do 45 if you want, but you don't need to be to have a very accurate angle. And you fold back the same way. Okay. I made 2 folds, this one and this one, and this looks like that. Okay. And if you unfold, you have 2 inclined lines. Okay, which appears. It is useful to reverse the fold to mark better the lines. Okay, so you can reverse the fold, so you will see better things. Okay. Voila. So and now you unfold everything, and you see what happens. It's a chevron pattern. Okay. I hope this is. Alright. And now the trick is to give the shape to to that. And it's difficult to use words. Let's start. You start with one of the line and you fold it this way, and you follow this line all along the zigzag line. You try to fold the same way. Let's say I started with a mountain fold here. It's a mountain fold with opposite to a valley fold. So I start with a mountain fold and I follow the zigzag line. Okay, and I try to follow all along the line, all through the paper. Okay. Now you do the same trick on the other line, but you must have a reverse fold, meaning I was mountain, this one must be valley. So this is mountain, this one must be valley. And you follow all along the line, and I make it valley. Okay, once you've done that, you see that you have those zigzag valley and mountains, and it's rather easy to collapse all the thing gently, okay, to reach the fold. So you're forced to reverse some folds in the vertical lines. You need to they reversed in some parts of the fold, okay, in some parts of the sheet of paper, and then you can collapse everything and get the pattern.